Hey, it's Mike from Modern Retro Dev. I'm revisiting the compiler project I worked on earlier. This time, I'm doing benchmarking. Stay tuned. Hey everybody. It's been a few months since I've talked about this compiler project I was working on for these modern retro systems. And I spent the past month and a half rewriting this compiler, trying to make it better. I really appreciate all the comments people dropped in my last video on this. And one of them that stuck out was, hey, this is cool, where's the code? And I gotta be honest with y'all, it was really kludgy and really bad, and it was kind of done as quickly as possible, and I didn't really want to share that to the world. So a big part of this was me rewriting it so that it was more fit for human consumption, and by virtue of that, it now exists in a GitHub page that you guys can see. I'll make sure to put a link in the video. But anyway, before I, go on any more diatribes, let's just jump right in. I'll talk about it. All right. So here I'm going to talk about this compiler rewrite I did for my hobby compiler project. Now it's quite a bit less janky than last time. Now, you might be asking yourself, why on earth would you rewrite this? You just wrote it like 2 months ago. And, well, there's reasons. As a general design philosophy, you always want to start off by modeling your code using clay. And then when it comes time to actually ship your code, switch over to writing it as marble. That allows your development process to go much more quickly, and when you make mistakes, it's less costly, and it both from a time and effort standpoint. So in this case, my modeling clay was Python, and my marble is Rust. So another thing I wanted to do in this go around was remove a lot of developmental cruft. Excuse me. So I have a very organic development process. I don't really, at least if I'm writing code for fun, I sort of plan out what I'm going to do, but not to the nth degree. So I just try stuff and see if it works, and maybe it works and maybe it doesn't work. And if it doesn't work, then, I will tend to remove it, but sometimes I miss some of it and accumulates. Hence developmental cruft. If you are going through the process of rewriting your code, this is your opportunity to identify that cruft and remove it. So Another difference here is the consideration for multiple platforms. In my initial prototype, I was only really considering the X16 due to my familiarity with it, but as I now have a Foenix F256 Junior, this is another platform that I do want to actively target, so there are design decisions that you can make that will make the process of adding support for those other platforms easier. So I wanted to go ahead and incorporate that. Another side effect or thing I wanted to accomplish was to improve the code maintainability. A lot of this came about just moving from Python to Rust, but some of it's also how you decide to structure the code. So it's sort of a incorporation of lessons learned, and that allowed me to make the code better from the long-term standpoint. Now, as far as where things stand right now, I've already reached feature parity with the Python version, and this includes data types, unsigned 8-bit, unsigned 16-bit, string 8, array 16, and these, I'm going to say they're partially implemented. I've implemented the features I need to hit my minimum viable product, but these are the types that are in there currently. I guess there's also boolean. I should have mentioned that. I also have support for evaluations on both the U8 and the U16 data types. This includes checking for equality, less than, greater than, less than or equal to, greater than equal to, so on and so forth. Also added back in support for nonlinear operations, ifs, else, loops. And I also include support for a few math operations. At this juncture, it's only plus equals left shift, right shift, bit shift operations. Also, I have file write operations, which may seem a little weird to add them this early on with this few data types and features in here. However, I added that in because supporting unit testing of my code was very important to me. So there were a number of bugs that I fixed in this development process, and I hadn't seen them before. For one thing, there were 2 or 3 incorrect labels in my 6502 assembly that were just persisting unbeknownst to me. It certainly would have caused a lot of trouble later, but I hadn't seen them. And the reason I uncovered these is because formally I was adding in like the entire built-in function code block every time you compiled the vintage low language down to assembly, whereas now I'm actually checking which functions you're using and only including the base level of functionality. And in doing so, I uncovered that some of the little function code blocks were basically calling or redirecting into labels for other code blocks where they shouldn't have been. Pretty nasty bug. So I'm glad I took a more proper approach in the rewrite, and that allowed me to eliminate these. Also, this probably falls under the long-term maintainability category, but the code blocks were formerly just living inside of like a dictionary or hash table, or call it, where there was like that function code block name, and then there was like the block as a list of strings, and I would just basically tack those on. But I have since moved off those built-in code blocks into their own assembly source files. So here's an example of one of these built-in assembly code source files. As you can see, it just looks like normal 6502 assembly. And as I mentioned, I'm only conditionally adding them now. And if you use the print U8 built-in inside your code, it's very easy for me to identify that that's something that I need to include in there. However, in the case of this print U8, it does require a division by 10 and a multiplication by 10 built in as well. So I guess in addition, I basically have some additional comments that appear at the start of these built-in code blocks that allow you to conditionally include requires. And it's sort of like a very simplistic C preprocessor include kind of thing. Just identifies those recursively and tacks them in, and so when you compile your program, you get what you're looking for. Now, I've mentioned a number of times that I have sort of a minimalist set of features in here, and that's really because from the onset of this project, I had a problem that I wanted to run, and so I've really just included exactly the features that I needed so that I could run that particular benchmark. And like I said, it may seem hodgepodge, but features that I've included at this point are reflective of to reach that minimum viable product design goal. However, as a result, I can actually compile and run that benchmark. So I'm pretty happy about that. I mentioned this a little bit earlier, but one of the reasons I added file writing so early on in the process was so that I could actually effectively do unit testing for my generated code and the output from said generated. As a part of this, I wanted to include a shutdown function. There's a cool set of values you can poke into memory. You can basically shut down the X16 very easily. And this was handy for me because I could basically open up a file, write all the output of the functions that I wanted to test, and then cause the thing to shut down. So from a scripting standpoint, I could basically run a whole volley of different unit tests, all writing out their own like output file, and they could all quit immediately after doing their operations, so the next one could go on. This made automation easy. Very, very neat way to do it, if I do say so myself. So once you have this nice textual output from those unit test files, I basically used a Git repository to track them, and that allowed me to very easily check and monitor for regressions in the code. Because sometimes you can make changes to things and have unexpected side effects. In this circumstance, I can run one bash script, and it'll rerun through, and I'll have a whole new set of outputs, so if I mess something up, I'll see it very easily. I should also say that this did make it a little bit easier for me to do the release, because I did have that base of unit testing to sort of replicate. Now, as far as a sample of what this unit testing looks like, on the left here I have the unit test that I wrote for the unsigned 8-bit print function. This goes through all possible values of unsigned 8-bit integers and prints them out. And on the right hand side you see the output file that's generated from this. Obviously not the whole thing, it's long, but so I would track the code on the left and the stuff on the right, and I think I'm also tracking the generated assembly. Sometimes I do refactor what gets included in there, and I do want to see what happens. Maybe at a later date I'll jettison the unit testing out of this main repository, but for right now I don't think it adds too much. So I mentioned a number of times that I had a benchmark in mind for this minimum viable product, and the benchmark I selected was the Byte Sieve benchmark. This is effectively an implementation of the Sieve over Rastascenes, and I'm hoping I said that right, because this is being documented for posterity, but we're going to say I said it right and go with that. If you don't know, this is a popular benchmark from the early home computer era. It's popular because it doesn't require multiplication or division. Also happens to be very small and simple to implement. And among other things, this will test the performance of array indexing, which it's a pretty common programming paradigm, so why not? Here I have a cool GIF of the Sieve of Rastascenes, and I totally lifted this straight out of Wikipedia, so you're more than welcome to go check it out there. But let me explain how this algorithm works. Basically, we're going to start with the number 2, and we're going to iterate through the array, adding that value to sort of the index, and for each one of those locations we will mark it as something that is a multiple of that earlier prime number. And then we will go to the next, if it's not marked, we'll then go to the next prime number in the series, in this case 3, and then we will continue to add 3 to that array index counter or whatever, and then we'll mark all of those numbers as multiples of that prime, and so on and so forth. And so you can see when you finish this process and you're at the final number, at that point you will have basically, whatever remains, those are your prime numbers. So I mentioned that one of the positives of this is that it is very simple to implement. Case in point, here's a little Python Byte Sieve implementation. It's about 33 lines of Python, including some comments. In this case, it just goes up to, looks at the first 30 numbers. We found 10 primes. There they are. Pretty neat. Here's an equivalent implementation of that same Byte Sieve, albeit in my vintage low language here. Not exactly as concise. We're needing 88 lines here, but it does calculate and print out the same values. You can see the output on the right, straight from the X16 emulator. We got the right numbers. Now, the calculate up to 30, it takes like really no time at all, and this wouldn't really serve as a very useful benchmark. So I needed a larger number to crunch, and I wanted a big number, and I wanted to be able to include a implementation of the basic that's bundled with the X16. So part of this was figuring out how high I could go before I basically had like a situation. I was able to get up to 7600 with basic before it started causing problems, so that's what I selected as the top end. And to make this benchmark run a little bit longer to really show standout performance, I calculate it 10 times within a loop. And I ran all of these versions in the X16 emulator, not using the warp function, so it's running at real time as the X16 would do. And to the best of my ability, and I'm not a basic guru by any stretch of the imagination, but I did try to write these benchmark implementations as idiomatically as I could with the tested languages. So, now for the moment that I'm sure you've been waiting for, actual performance results. Boom. So it's a bit of a surprise to me, and I haven't mentioned this yet, but the fastest implementation I could come up with was actually with this language called Prog8. It's a pretty cool little language. It targets 6502, 65816 machines, and it is very optimized. It was able to do this entire calculation in 6.4 seconds, and just behind that you have the two C implementations. CC65 was ever so slightly faster than the LLVM MOS implementation, as far as I'm concerned, if you're compiling them with optimizations. And if you're not compiling them with optimizations, then they're appreciably slower. And right in between the uncompiled or unoptimized C implementations, you have the performance of the vintage low-level compiled version, which is what I came up with. And honestly, for only having worked on this like a month or two, and half of that was just refactoring to get to the same place, I honestly feel pretty good about that. I'm really quite in awe at the ability of these compiler designers to optimize code the way they do. I'm going to have to look into it a little more if I want to make it faster, but for right now, I feel like this is a pretty cool situation. Also, I did mention that I wanted to include BASIC in here, and BASIC is very slow comparatively speaking. And it's neat and notable because it's the only interpreted language implementation of this benchmark that I've included here. Another fun thing here I included is relative performance. Prog8 obviously runs at 100% speed of it being it's the fastest code. Stepping down from that, you have the CC65 running at 97% performance, LLVM MOS C at 95%, and scooting down to what I wrote, 24%, and finally you've got the basic performance at 0.6%. So yeah, I honestly thought that was surprising, cool, fun, all of the above. So I think that's a pretty good summary of where the code sits at right now, and it's a project that I'm pretty excited about, or that's just kind of where it's at this moment. And I do have additional plans, and if you do check the GitHub project, you'll see them there. But for people who don't want to check that, let me go ahead and talk about it here a little bit. As far as other ideas that I'd maybe like to consider pursuing, the first of which I already mentioned earlier in the video, which is to target additional platforms. The first thing I'd really like to look at is the Foenix F256 platform. I've got this hardware, I need to use it and play with it, so that's going to be the next one I work on. And after that, a platform target that I think would be really interesting would be to compile vintage low-level language into C. And the big takeaway there is I would then be able to compile the outputting code on like modern Linux and Windows machines, and that would be pretty cool. And if this whole benchmark has taught me anything, it's like very hard to outperform modern C compilers. So we're going to generate C and we will just roll with it and it's going to be great. So that would be cool. Another thing I would like to try my hand at is writing a little 6502, 65816 assembler that I could just include in along with this project. Because what I've been doing thus far is piggybacking on the CC65 assembler, which is cool, but I really would like my code just to be like a one-stop shop where you just grab it and you can compile and just directly spit out programs. That would be ideal in my opinion. And it also may make it a little bit easier for me to support other platforms. So that's a consideration. Another thing I'd be very interested in doing is writing a self-hosted compiler. And as I'm sure you could tell, I was very impressed with the Prog8 language. Very surprised by the performance benchmarks on that one. The only thing I'm seeing here is Prog8 as a language. It seems like a very complex language to parse. And also, it's very highly optimized. So I'm not sure how conducive that particular language would be towards like a self-hosted compiler. And I'm not here to say it's impossible. I'm sure some wizard out there can do it. But for me, I'm a simple man. I think the language that I came up with is very simple. And I think by virtue of that, it would be pretty simple to write a compiler for it. So I think that would be kind of an interesting option. The final thing that I was thinking about in this like line of projects, I'm sure you've heard me call this little language I've been compiling vintage low level, and it's always been my plan to do a higher level implementation of a language. I mean, I saw the source code just as well as you did. It's okay, but it's very verbose and it doesn't have any of the modern niceties. So I think it would be cool to make something that's a lot more simple and modern to program with, and basically have it compiled down into the vintage low level, and so on and so forth. I think that would be pretty cool. So anyway, those are some of the ideas that I've got right now. But I would be very interested to hear what your comments and feedback are. Like, specifically of these like 4 other ideas I'm thinking about, which do you think is most interesting? Or maybe like give me an ordered list of best to worst, or you've got some other idea I haven't thought about, and drop it in there. I want to know. Anyway, there's a lot of other things I could talk about, but I'm already running a bit long. So I think I'm just going to take this as my cue to get back to some modern retro dev. Take care.